A very good day to all. The topic being discussed today is the Heck reaction or the Mizrachi-Heck reaction. It will be undertaken under these following headings: introduction, mechanism, regio and stereochemistry, applications, and limitations. So, as far as the reaction goes, it's a very important cross-coupling reaction for which Heck, together with Suzuki and Negishi, was awarded the Nobel Prize in the year 2010. The reaction is as follows, where an aryl or a vinyl halide, it reacts with an alkene in the presence of palladium and a base to give us the coupled product. This is cross-coupling R1 and R2. As we can see, R1 is it can be an aryl or a vinyl group, and X can be either any of the halogens, iodide, bromide, chloride, or a triflate. Anyone interested in this can further study about this very interesting reaction, which led to a chain of researches, and work is still going on. You can see a number of treatises on this subject and the progress that this reaction has made over the decades, because it's very applicable and very useful and a very convenient method to prepare these type of coupled products, which are basically, it has a great outstanding trans stereochemistry. The reference is as follows: Deek, H.A., R.F. Heck, published in the Journal of American Chemical Society in the year 1974. So you can read up this reaction in detail. You can read up about the reviews, various reviews on this, and the additional work which has been going on and still going on this type of a catalysis, and various modifications like the Sonogashira. Various modifications to this are also there in line. So let's start with the mechanism. The mechanism, see, first of all, we'll just outline the mechanism before exactly understanding it. As was dealt with earlier in the case of Sonogashira reaction, the pre-activation, we all know that palladium-2 is converted or activated to palladium-0, because palladium-0, the zero-valent palladium, is unstable. And this can be, so this pre-activation of the catalyst can be conducted in two ways. The outer shell mechanism. The outer shell mechanism, as has been told here we can see the ligand attached to palladium-2 along with this triphenyl phosphine. In the outer shell, this acetoxy group is not present along with palladium. So this is called as the outer shell mechanism. This leads to the zero-valent palladium along with this, which is further, this compound which is further hydrolyzed to triphenyl phosphine oxide. And the inner shell, now the inner shell mechanism. Here, as we can see, in the inner shell mechanism, this acetoxy group is linked with this palladium. So it is called as an inner shell mechanism. Of course, there will be an hindrance because these two groups are present. It's proposed that the outer shell mechanism, this one, is more favorable for producing palladium-0 rather than this inner shell. So, but this also operates. And of course, in this case, what happens when this type of a compound is selected, a pre-catalyst is selected, in that case, after reductive elimination. So, we are going from valency, this 2, to valency 0 for this, the zero valent again we will get this 0 valent palladium along with, as indicated earlier, the phosphine being oxidized. So for the mechanism, the pre-activation of palladium takes place by two mechanisms, outer shell and the inner shell mechanism. Now let's move on in the mechanism to the next step, which is the oxidation addition. Oxidation addition, it is the most difficult step. The most difficult step, why? The breaking of Rx, and secondly, this bond is broken, Rx bond is broken, and secondly, formation of PDR, and at the same time PDX. At one side R is attached and the other X is attached to this palladium catalyst. This takes place, and the rate, as has been discussed earlier prior to this in the Sonogashira reaction or the coupling reaction, similar to this. In this, of course, there were two cycles in this. In that case, the copper one and the palladium one. So the rate is determined by these halides, the nature of these halides. Iodide being more reactive than triphthalate, being more reactive than bromide, which is more reactive than the chloride. Now, as far as the mechanism goes, after this has been accomplished, then only the olefin addition and insertion takes place, and it's a syn addition, we will see. Very interesting syn addition, and it's a migratory insertion, because once this insertion has been made, then the catalyst and the product, they just drift away from each other, they migrate away from each other. That's why it's called a migratory insertion. As palladium complex, and they all, the two of them, the product, they migrate or move away from each other. And the addition has to be syn, remember. Syn means the palladium, the catalyst complex, which is formed, palladium catalyst complex, which is formed, bicomplex, that, and the aromatic ring on the other side. They are present syn above the alkene. We will soon see how, by virtue of this, certain things occur, like it is by virtue of this, we can say rather, that the stereochemistry is controlled, and we get a very interesting trans product. As far as the regioselectivity goes, regio implying the structural, because see, this is the alkene bond, this alkene double bond. So the coupling can occur either at this position or at this position. That is this position, which is alpha to pH, this phenyl group, or beta. The less substituted, this CH2, or this more substituted. Either of these. That is, the R can attach R, which can be either aromatic or vinyl in nature. This R can attach either here or here. That is, so a set of structural isomers can be formed. Now, which of the two predominates, or what is the ratio? That is decided whether the complex, the palladium complex, is a neutral complex. Now, what's a neutral complex? When palladium complexes are present with the halogens, that is chloride, bromide, X is equal to Cl, Br, or I. In that case, it's called a neutral complex. So, see how the regioselectivity works. R will be attached 100% at this. Rather than this place, R will be coupled at this place. If this is the structure, in this, here we will get 80% of the structural isomer, that is R will be coupled here and 20% here. In this case, R will couple here 60%, this is the ratio, and 40 here when this happens to be the structure. This is the case of neutral complexes. In cationic complexes, what are cationic complexes? When in that case, X is equal to OTS or OAC, acetoxy or this, tosylate. So in this case, what happens? In this case, we get 60% ratio here of the structural isomer. That will be when we get the coupled product, then 60% coupling R will be here. In the other structure, 40% we will get the product R placed here. In this case, 95% R will be here. and at the same time 5% here. If this is the structure, in this case, at this position, 100% of, so CH2 here and 100% of the RR attached over here in this way. So this is the case when we are talking about the regioselectivity, as far as the regioselectivity goes. Now coming to the beta hydride elimination. The beta hydride elimination, after alkene and palladium, they have attached to each other in a syn manner. The insertion has occurred in a syn manner. Then palladium and hydride, they should be present syn, because palladium together with hydride, they are the ones which are detaching. So that basically, so the product is a trans alkene, and the reaction is an outstanding trans, having outstanding trans selectivity. Now after this, the regeneration of the catalyst occurs. How does it occur? By a base. The regeneration, that is palladium 4, is again converted into palladium 0 valent, and that takes place in the presence of a base, because the base is the one which takes away the H positive from it and the X negative. So H and X, they are with the help of the base, of course. So a salt is formed, and at the same time the PD0 catalyst is regenerated. This is the cycle, the Heck mechanism cycle. This is a very interesting cycle. We will these are now the points which were discussed earlier, which you must have noted. Now let's see how, according to those points which we have understood, how does the cycle operate. So having a closer look, this is now palladium, the pre-catalyst. The pre-catalyst by reduction gives rise to PD0 by reduction. Remember, because that is PD2, this is PD0. Now this PD0 is the one which now is in an oxidative addition. As if you recollect earlier, the features are common because with the Sonogashira, because there too itself we were taking the palladium catalyst in the 0 valence state. So if you correlate with that, and if you were able to understand that a little, then this is simpler than that, because 2 cycles are not operating. As I mentioned earlier, only 1 cycle is operating in this case. Now this aryl halide adds to this palladium 0 valent in an oxidative addition way. As a consequence, what is formed? PDL2, of course, these are the ligands. And at the same time, as we can see, at one end there is AR, at the other there is these two, the X or the halide. Now this, by virtue of this reversible reaction which is shown, because ligands are continuously, they can detach, they can be attracted, they can migrate away, that sort of a thing. So here we get AR, PD, X, L. And this L is of course at the same time present here. The ligand is present with palladium. But why? Because, gradually it is being drawn towards the spool of electrons. That is our alkene group. The alkene and the palladium, they together form this type of a complex is being formed. This type of a complex is being formed. We can see palladium, the aromatic ring, the halide, the ligand on palladium, slowly, gradually attaching to the alkene in a syn insertion. So it is a syn insertion. The syn insertion occurs in such a way here, as we can see, because this syn insertion is occurring. This is the sawhorse projection. The sawhorse projection in this you will be able to clearly make out that the aromatic ring and the palladium, the aromatic ring, this AR, it could have been vinyl, it could have been aromatic, because here we have taken an aromatic halide. This is on the same side as this palladium complex. So this creates a torsional strain, these two bulky groups on the same side. With the result, what will happen, if you remember some of your stereochemistry and the diphenyls, this carbon-carbon single bond rotation, it is similar over there too. So this rotation occurs so that this aromatic ring will move away from this palladium complex so as to lower the energy of the system. With the result, what will happen? As a result of this internal CC rotation, the CC rotation occurred. So see, this aromatic ring has moved to the opposite side of this palladium. With the result, this hydrogen is now on the same side as this palladium. That means, in other words, now these two can therefore in a way promote beta hydride elimination. Beta hydride elimination, because hydride means implying that this hydrogen takes this electron pair towards itself. This palladium leaves this here, this link which has been formed. So a double bond will be formed between these two carbons, which at one end has this aromatic group, at the other end has this alkene, this group, R, alkene. As a result, this compound is now gradually, the product is being formed, AR at one end, the double bond being formed, palladium migrating away, the R trans to this aromatic group, and as this happens, we get this product, that is, the Heck product is being formed, outstandingly trans in nature, E. This is an E product formed as a consequence of this syn complex formation earlier, because the insertion was syn, the product was E, trans. And again, we are getting this complex, the palladium complex, the PDHXL, PDHXL, along with this L, with the help of this base. This is the base which is present, and this base is the one which is able to help this palladium to once again regenerate or change into the palladium 0. The H and the X leave in the form of H positive, X negative, which is stabilized by this base, and this is PD is now left with just these two ligands and converted, or this palladium 0 complex has been regenerated. I hope you will be able to recollect this cycle. How? Let's see. This palladium pre-catalyst changing to what? The palladium 0 valent. That is the main catalyst. This undergoing oxidative addition to form this complex, this compound rather. This with the help of this alkene now changing into this complex where it is being a syn insertion. A syn insertion implying that both this aromatic and this palladium complex, they are on the same side, that is adsorbed on the same side. PD at one end of this double bond and AR at the other end of this double bond. The double bond has opened up, but it is syn, remember. Because it is syn, it is not energetically favored. Hence, there will be a carbon-carbon single bond rotation. As a consequence of this, the energy of the system will be lowered, because now the two bulky groups are the aromatic group and the palladium, this compound, this complex. They are away from each other. This will give rise by means of syn beta hydride H negative elimination. So this H will be attached to this PD. This bond will form a double bond here, and we get this completely trans product. Palladium with the two ligands, the H, that is the hydride, the X, which was attached earlier only since from the oxidative addition step, and this is now regenerated with the help of the base to form or give us back our palladium 0 valent. Now coming to the applications of this very useful reaction. The applications are rather interesting. In sunscreen, the compound which is used, that is octyl methoxycinnamate, this is used there for the synthesis of octyl methoxycinnamate, the sunscreen compound. Naproxen, which is this compound which is a non-steroidal anti-inflammatory drug, and which is used for relieving the pain in arthritis, etc. Naproxen. So naproxen, and it is besides this Chantis, this compound, this Chantis, it is used for smoking cessation. This sesquiterpene lactone is used in leukemia. It is used for the synthesis, this method, hex synthesis. And at the same time, hex synthesis is also used to produce thinner circuit boards for smartphones. And this technology is now being used for coupling fluorescent dyes to DNA strands for human genome mapping. A very interesting application of hex coupling. So these are the applications, and last but not the least, of course, are the limitations, as we have been saying even earlier, that limitations discussed last. Now palladium catalyst, because there is loss of palladium catalyst at the end of the reaction. Why? Because many a times it's difficult to separate it from the compound. It gets incorporated and separation is difficult, and at the same time it is also expensive because this uses nanomembranes, so it's expensive also. And phosphorus ligands, of course, as we all know, they are toxic as well as they are expensive. So this was all about hex coupling reaction, and I hope you were able to follow. We will soon be doing some assignments based on these.